Okay, today this is a lesson over moments. And moments aren't a thing about time in this situation. They are a thing about a force. What kind of force? I've said it a couple times, but a force that has a tendency to rotate the body upon which it acts. So it says here the moment of a force is a measure of the tendency of the force to rotate the body upon which it acts. And I think the greatest example that can be used is a wrench. So this wrench has a force that is acting upon it at the end of it, and it's turning the bolt there. So let's look at some terms that are going to help us calculate moment. We have the distance must be perpendicular to the force. So that's a very important fact about moments. So we have a force and we have a distance. Now it's perpendicular, so this force would be going this way where the distance is traveling this way. Kind of think of the distance as like a line on an axis, so this would be a line on X, and the force would be a line on Y, so there's perpendicular. As you can see here, now this is kind of messed up, so let's take a look at that. It says moment. So what is it trying to say here? Basically, moment is, oh, well, this box is too small. Let's see. Delete that. Moment is a force times a distance. And distance will be like this. And we'll go ahead and do it like this. Force times a distance. And the distance has to be perpendicular. So I don't know, sometimes they do that with like a line or something above it, but the perpendicular distance. If it was force times the distance, it would be work, like distance parallel. Meaning I'm pushing a refrigerator, remember, in that same direction. I multiply the force by 250 pounds of force, multiplied by the distance that that refrigerator traveled. And then you can say, hey, it traveled 30 feet, 30 times 250. And you'd have that as your work. Now here is the units that we're using. So in that refrigerator example, you'd say, okay, this many pounds of force you have traveling in 30 feet. And then we'd say, okay, force. We'd say pounds per foot. So pounds of force per foot. There's also we actually have Newton meters too. So English customary Newton meters. We have the metric system as Newton meters. So they're both a force, newtons or pounds, and they're both a distance, foot, feet, and meters. And then when we're rotating, we're talking about a counterclockwise and clockwise. Now it's kind of, you would think almost clockwise, you'd say that's positive, but counterclockwise is actually positive. And you can kind of think of this like back at the force vectors lesson when we had a vector being pulled on the x-axis. If that vector was being pulled at a different degree from the x, it would be, if it was counterclockwise, it would actually be positive. You'd be entering the first quadrant, which would be, hey, we're moving up on y, which would be positive. If you're going counterclockwise from the x-axis, you'd be starting to move downwards on y, and you'd be in the negatives. Okay, here's this rule that's supposed to make things easier for calculating positives and negatives. And sometimes it can make things more confusing. So it's called the right-hand rule, and curl your fingers to match the direction of the rotation. So I have my right hand, and that looks, okay, my right hand, and I'm going to hold it like this, okay? And you can kind of picture yourself looking down at a paper, and you have a wrench that's rotating a point. Now you have to line your fingers up to where the curl is lined up with the way that the wrench is going to rotate based on the force. And the thumb is pointing up towards you if you're looking down at the paper, or down, like, because you're trying to match the curl of your fingers with whatever direction that it's moving. And if you are matching the curl of your fingers, like your fingers are pointing to the direction that the wrench would be turning, then okay, I know that it's going to be negative because it's going clockwise, and my thumb is pointing down away from me. If I'm pointing up, then this is going to be positive. So that's what it means. And it's going to go over that a couple times in this next slide. So, all right. So here's a force going down on this wrench here. If you have your thumb and you're looking at it and you say, okay, my fingers line up and they're actually matching with the way that this thing would be turning, it's going to be positive. Okay, I'm going to have a positive movement. It's counterclockwise. Okay. Okay, negative. So if I'm going this way, it's going to be negative. Now, my thumb's pointing away from me. I don't know. Right hand rule. Okay, so why is this important though, negatives and positives? Well, if you look at this right here, when we're calculating moments, I have a force of 20 pounds here, and then I have a distance of 9 inches. And remember, that's inches. And going back to the units, well, we're not dealing with inches here, we're dealing with feet. So you're going to have to do some basic division to come up with, hey, 9 inches is 0.75 feet. Or a foot, 0.75 feet, yes. So what is that? So if we're going back to what a moment is, you're going how to calculate a moment, your force times your perpendicular distance. Now this is perpendicular because it's going on the x-axis. You can kind of think of it like that, and the force is going on the y-axis, and you say, okay, it's totally perpendicular. We have 20 times 0.75, but it's negative. Is my answer going to be negative? Yeah, your answer is negative. So you have a negative moment there because my right-hand rule, I'm like, oh, if I do this, I'm pointing away from me. So it's a negative 15 pounds force, or pounds, foot pounds. Okay. Same thing here, except for they're just doing 1 foot. Okay, so it's a 1 foot exactly, 20 times 1, 20 pounds feet here. And I'm going to say force pounds. I'm going to say pounds feet just because I'm saying the 2 units. It's a pound and it's a foot. Okay. Here's an example of an L-shaped wrench and how it really shows off the perpendicularness of a moment, I guess. So if we're saying, okay, here is our rotation point, here is our force. Well, this distance right here of the foot is parallel to that force. So that's not even calculated in the moment. The only distance that's calculated in the moment is this 3 inches because that's where the force is given. That's perpendicular to the distance here. And this would be like this distance of this L shape here. So it's 3 inches, which is 0.25 feet. You multiply that by the amount of force, the magnitude of force, and that's 20. Well, which way are we rotating here? Well, rotating clockwise, right hand rule, this is going to be negative, so it's negative pounds feet here. All right, here's an example of Z-shaped wrench. The only distance that matters in a moment calculation is the perpendicular distance. So 8 inches, 10 inches, those are perpendicular to the force right here. So you could say, okay, we're going to add 8 and 10. Okay, that's going to be 18 inches. What's that? 1/2 feet. I don't think that's exactly right, right? Oh, yeah, it is. Okay, well, 18 inches. Then you multiply that by 20. Then you're left with traveling. We're going clockwise. So this is negative 30 pounds per foot. There's a moment. That's a moment calculation with those wrenches. Now, what about other things like wheel and axle? Those are still able to calculate moment because you're rotating. So if we think about, I guess we're using maybe we're pirates now, and we're steering this old, I forget what they call pirates wheels, but okay, there's a force of 100 newtons here, and what's the distance away from the fulcrum or the rotation point? Well, notice that we're dealing with newtons and centimeters now, and the unit for this was Newton meters. So we'd actually have to calculate and say, oh, we have to turn centimeters into meters. Well, for a lot of us, that might seem like, oh, that's more difficult. But really, remember, it's not because we have centimeters, we're moving the decimal twice over and saying, okay, so 50 centimeters is going to equal 0.5 meters. Okay, so now we're just doing the same calculation. It's the perpendicular distance times the force. Okay, so we have 100 times 0.5. We have 50 Newton meters. And before you go, well, how do we decrease? Now, this is positive because it is traveling counterclockwise. Your right-hand rule, you go like this, you're pointing to yourself. But you'd say, okay, wait, I have 100 newtons on this thing. And am I losing torque? Am I losing force? No, you're not. You're actually increasing because Newton meters is a different unit than meters, or than newtons itself. Okay, so moving on to the next slide, we have the same thing, but here's where force vectors matter. So we're still dealing with the moment, and we only care about the force that is perpendicular to, or the distance that's perpendicular to our force. Okay, they need to be perpendicular. So we're determining the force here, and we care about the perpendicular force to the distance. The distance is remaining the same at 50 centimeters or 0.5 meters. But going back to force vectors, we're only going to care about the force at y, okay, because that's the only perpendicular force to this distance here. So we have 100 newtons being pulled at this angle from y. That's 50 degrees. So we have to take the sine of 50, because we're dealing with an adjacent side right here, because it's the force at y. So the sine of 50 degrees, and then you multiply that by the perpendicular distance. So the sine of 50 degrees, you can see, is 0.766. You multiply that by the force, the hypotenuse, so 0.766 by the force, the hypotenuse, 100 newtons. You're left with 76.6 newtons. And then you multiply that force, because that's the only force perpendicular to the distance, multiply that by the 0.5 meters, and you're left with 38 Newton meters. So even if your force is not totally perpendicular, you can use the force vectors to come up with the perpendicular force. Okay, so this is going to start talking about equilibrium, because we're going to move from this section to trusses. So it's going to be important to realize what equilibrium actually means. And I'll just read off the slide here, and we've talked about this before, but the state of a body or physical system with an unchanging rotational motion. Two cases for that condition. The object is not rotating, or the object is spinning at a constant speed. In either case, rotation forces are balanced. Okay, the sum of all the moments about any point or axis is 0. Okay, so we have the sum of moments is equal to 0. We have moment 1, moment 2, moment 3. They're all adding up and they're equaling 0. Okay, here is a seesaw example with the two teddy bears, it looks like here. One's bigger than the other. And we're looking at it and we say, okay, this seesaw currently is balanced, okay? It can rotate, but it's currently balanced. But we have a smaller bear over here. So the distance is going to be the only impact, or going to be what impacts how it's at equilibrium, because we have a 25-pound bear and a 40-pound bear. Man, that's pretty heavy. Okay, so the moments have to equal 0. So we know that the distance of the smaller bear is 4 feet. Well, what's the distance of the large bear away from the fulcrum, or the turning point? Well, this is algebra, right? We could do 4 times 25, and that's going to equal what? 100, right? So 100 is equal to 40 times what perpendicular distance? And that ends up being 2.5. So the distance of the, I guess you could say, of an effort arm or whatever, distance 2 is 2.5 feet. That's because it's at equilibrium, and you can say what distance would make this at equilibrium. And here is another example. This is a beam. We have a gift here, a 35-pound present. Who knows what that is? And we have 2 reactionary points here. We have a reaction point at A and we have a reactionary point at B. They're both on the y-axis. So this is at equilibrium because the beam is still remaining up. It's not falling down or anything like that. It's not moving. And there's a gift, a 35-pound concentrated load 3 feet away from A. Now the total beam distance is 10. So what's going on here? Well, this is actually calculating how much force. We're actually doing something a little different where we're saying we're not trying to find out like what the distance is. We're trying to find out how much of the force here is being traced back to A and how much is being traced back to B. Now, this is where it is more logical because we have 2 points that are supporting this present. And it's not like, okay, we have this force. Generally, if this was not here, right, if the A was not supported and B was the only thing that was supporting it, you'd say, okay, the farther the gift gets away from B, the greater force it's going to have, right? But because it's supported here, more of the load, just common sense wise, is traced back to A than B. And it is proportional to the distance here. So let's take a look. So if we have, okay, we're going back to some of the moments were equal to 0, we're at equilibrium. And this is lowercase d, so it's a distance AB, that means the distance from A to B, times the reactionary BY is equal to the distance at AC times the reactionary point at FC. So this point, the present. So we're saying right here that this distance here multiplied by this force is equal, because we're at equilibrium, of this distance and the reactionary force at B. They have to equal each other. So we're taking 3, the distance from the gift to A, 3 feet, times 35, and that's going to give us a point, a certain force at A, and then B has to equal that because it is a moment and has to equal 0 for it to be at equilibrium. So looking at it, we're saying, okay, we have 105 divided by 10, because that's the total distance, has to equal 105 right here divided by 10 has to equal 10 times the reactionary point at B. So we're left with B, reaction point at B being 10.5. So right now, you could see that, hey, the reactionary point at A, reactionary point at B has to equal 35. We know that the reactionary point at B is 10.5, then we know that we're left with 24.5 at A. Okay, this is the second to last slide, and this is dealing with trusses now. So we have a free body diagram. Well, it's not really a free body diagram completely yet, but what we have is we have forces that are, we see the forces acting on the truss system here. We have distances of the truss. We have the reactionary forces are in green, the green areas, and the forces themselves, the loads, are in red. So they give us a load at point C and they give us a load at point B, and you can see that they're headed different directions. So we also know that A is pinned and D is a roller. So D does not have a reactionary force on the x-axis because it's meant to roll on that. Okay, so what does that mean? Well, then we're going to calculate the rotation. We're going to calculate the moment at D. So we're actually going to figure out what the reactionary force is at D. So this thing is at equilibrium. That's the important thing to know. So it's supporting all the loads on here. So that's what we're going to go through right here. So the sum of all the moments have to equal 0. That's just saying it's at equilibrium. Okay, the moment at D is equal to the moments at B and C. So we're going to calculate the moments at B and C and see what we have. So the lowercase d, again, is the distance. So the distance from A to D is going to be multiplied by the rotation, or the, sorry, not rotation, but the reaction at point D. So again, that's the moment, right? Because we have A is the rotation point. We have this total distance of 32, and we're going to multiply that by whatever D is, and that's going to equal the rest of the forces because it has to, because we're in equilibrium. So what is that number though? We don't know. So we're going to calculate the moments for the other ones. So the moment at B, the moment at, yes, B is the distance from CB, which is 12 feet, times the 500 pounds, plus the reactionary moment, or the moment at C, the 24, A to C, the distance from A to C, multiplied by the 600-pound force. Okay, when we add those up, the 6,000 plus the 14,400, we're left with 20,400. And then we're going to divide that, because now we have 20,400 is equal to the reaction at D times 32. So just algebra, we divide 32 by each side, and then we're left with the reactionary moment at D is 640 pounds. All right, I hope this makes sense. And if you have any questions, just email me.